Hello world, welcome back to LeetCode Legends. This is Brian, and this week I'll be going over Permutations, LC46. Check out these sweet permutations of this superhero in different multiverses. So to start off, let's go over the question and make sure we understand it. You're given an array nums of distinct integers. Return all the possible permutations. You can return the answer in any order. So here we have an example input of nums equals 1, 2, 3, and there are 6 different permutations that are formed by considering any possible ordering of those elements. So let's go back in time to 7th grade or whatever math class. How many permutations can there be? So there was this magic equation we were given. I always forget, I always have to look it up. NPR. So given n elements, if we're to choose R, we have this formula to calculate the total number of permutations. So we have, in this case, we're always going to choose n equals R, or R equals n. So for example, if n equals 3, there's 3 elements. 3 minus 3 becomes 0 factorial there in the denominator. 0 factorial is 1 by definition. So it becomes n factorial for this question. And so if you have 3 elements, there are 3 factorial permutations. And so it's 6, as in the initial example. If you add one more element, so you have 4 different numbers, then 4 factorial becomes 24. So you can see that this will scale very rapidly, right, by a factorial. So our space complexity and our time complexity will be related to n factorial. Now, the great John Lennon once had a song that went, "Imagine all the people living life in graph." And that's one of my favorite songs. So oftentimes when I see a problem and I'm not sure how to start, I think about, could I represent or model this problem as a graph and use graph algorithms to solve it instead of like reinventing the wheel? Because I know my graph algorithms. I may not know how to solve every problem in the world, but I know like depth first search and breadth first search. So let's think about depth first search really quick, just in case you haven't seen it in a while. So this is pseudocode copied from my textbook. Sorry, I forgot to cite it here. So depth first search is a function that's given a graph as input. And for all vertexes in the graph, it sets a visited array to false for every vertex. It could be an array or it could be a set. I like using an array if I can get away with it. And after initializing that visited array, for all vertexes, if that vertex is not visited yet, explore starting from that vertex. So explore or search starting from vertex V. All right, so now you have to understand what is explore. So explore is a subroutine of DFS, and it's given a graph G and a starting vertex V. Mark that start vertex as visited. Then, for each edge from that vertex to a neighbor, if the neighbor is not visited, explore from that neighbor. So you're going to be searching depth first through a graph, going from a start node to one of its neighbors, to one of that node's neighbors, to one of that node's neighbors, on and on and on until you can't go any deeper. And then you'll bounce back up the call stack and eventually explore other children of the same node. All right, so Here, I've taken the original question, which had 3 elements, right? 1, 2, and 3. And instead of using the values, I'm just going to use the indexes, because the indexes are going to be unique for every element no matter what. Even though this question, it said, we have distinct integers, so you could get away using the values. But I'm just going to use the indexes because it'll be easier, and I can start from 0. So I have a graph here representing the original example, and note that it's fully connected. So there's technically 6 edges here because they're all double-ended. There's an edge from 0 to 1 and 1 to 0. And if you think about this graph and think about all the paths through it, that might also tell you the number of permutations of these elements. But before we get into that, let's review how DFS will behave on this kind of graph. So I'm using a color scheme here. Blue is unvisited, gray is a visited node, and black is a node that's been fully explored. And so we're going to mark it explored and then bounce back up the call stack. I'm also going to keep track of the path that DFS has traversed as we go through this. So let's start DFS. DFS will visit the first unvisited node and start exploring. So we're exploring here from node 0, and we're going to mark it visited. We add that node to our path, check the first unvisited child of node 0, and explore there. Mark it visited. We add that node to our path, check again for unvisited children of node 1 now. We're going to go depth first, and we see it, and we go explore there. Mark it visited and add it to our path. Now we're going to check if node 2 has any unvisited children. It doesn't. And so we're done exploring node 2, and it's fully explored. Mark it black. And now we're going to return up the call stack. So we go back to where we were. Looking at node 1. Does node 1 have any more unvisited children? No, it doesn't. So mark it fully explored. Bounce back up the call stack. Does node 0 have any more unvisited children? No, it doesn't. Notice that node 2, we never went from node 0 to node 2, but we're not going to because we already went to node 2 from node 1. So we mark node 0 fully explored, and we went on a singular path through the whole graph, 0, 1, 2, and explored every vertex, and we're done. So DFS completed. Single path was found. So keep in mind that there was an outer routine that was iterating over all unvisited nodes, and in this case that outer routine only had to run one iteration because a single explore call recursively visited the entire graph because it's fully connected. Alright, let's put our thinking caps on here. What if I want all paths, not just one path? Can I modify these classic routines to search through all paths possible? You might have to unvisit some nodes after you finish exploring them. I'd love to unvisit my in-laws, wouldn't you? So the visited set or the visited array is the only thing that stops you from going multiple places, right? And normally you want that in DFS because you want to be efficient about what you're doing. But let's take a look at what would happen if we mark a node unvisited. So before we were marking nodes explored when we fully explored them and explored all their children. Now instead of marking explored, let's mark it unvisited and see what will happen. So DFS starts exploring from node 0 and marks it visited, adds it to our path. Check the first unvisited child of node 0, finds node 1, and we start exploring from there. Mark it visited, added it to our path. Keep going depth first. We explore from node 2, mark it visited, add it to our path. Now, we found a path of length 3, so I'm going to add it to our paths array. This is an array that will keep track of the total number of paths we traverse. Now, here's where something changed, right? I'm not going to mark this explored anymore because I want the opportunity to travel through this node again if I can find another path to it. So now we bounce back up the call stack to node 1. Node 1 doesn't have any other children that are unvisited besides node 2. And we're not going to go look at that node again because we already went there from node 1. So again, we're going to mark node 1 unvisited and bounce back up the call stack. Now here's where something drastically different happens. So we've bounced back up the call stack to our starting node. We started exploring at node 0. Now node 2 is unvisited. It's a child of node 0, so it's a valid path that we can go now. And so we're going to recurse and explore from node 2. Node 2 will be marked visited and added to our path. And we go to node 2's first unvisited child, which is node 1, mark it visited, add it to our path. We found a new path of length 3 through this graph. It also started at node 0, and what we have here is 0, 2, 1. That's the path we just took. So we found 2 paths. We're going to now bounce back up the call stack and mark everything unvisited on the way back up. So what's interesting here is we found all paths through this graph that started from node 0. We've also found all permutations of the original array that start with index 0. So 0, 1, 2, 0, 2, 1. The outer loop of DFS will continue iterating, right? It considered node 0 as a possible start location, and now it's going to consider node 1. And for the sake of time here, I'm not going to walk you through iteration by iteration, but what we will get eventually as we complete all these traversals is we will find all possible paths through this fully connected graph, and these correlate exactly to all possible permutations in the original array. All you have to do is dereference the array, so nums0, nums1, nums2, nums0, nums2, nums1, and so on. Victory is ours! The great Genghis Khan once said, "Elegant solutions that work are nice." So let's code this. The time complexity of this solution is O of n times n factorial, because there are n factorial solutions, and it will take O of n time to copy each one into our resulting solution space, right? Our permutations array, if you will. Okay. So I'm going to try to stay really close to that pseudocode that I shared earlier on. And what we're going to do is define an array to hold our permutations. and we're going to call depth first search. Depth first search is passed a graph as argument. We're just going to pass in nums because that is our graph, and we're going to fill out the permutations array along the way. So let's start implementing this DFS function. So it's going to take its argument, the graph, and the permutations array. The first step from that pseudocode was to initialize the visited set. I'm going to use an array for it though. So visited equals false for I in range length nums. So that was the first line of pseudocode. Now we're going to do the next one, which was to iterate over all possible starting points, and if that node is not visited, we're going to explore from that node. So for I in range length nums, if not visited, I explore the graph starting from node I, and I'm going to need to pass in a couple of things here. Path and paths. So I'll explain this in a second. So I'm going to rename the permutations argument here to paths, because once I'm inside of the DFS function, I want to think about a graph, and I want to think about the path that I'm currently traveling and all the paths that I've found. So this is it for the DFS routine. I initialize an empty array path here because every time I call the explore function, I want to record the current node that I'm visiting into this array, and this is how I'm going to build up and keep track of the path that I'm traversing. So now we need the subroutine explore. So explore takes as argument the graph, the index that I'm visiting now currently, and the path that I'm building up, and the paths that I've found. Per that pseudocode, the first thing we should always do is mark a node visited. So visited, oh, I should pass that in. Sorry about that. Visited equals true. It has now been visited now that we are here. I'm also going to record the node that we're visiting. So we're visiting node I, and I'm going to get the actual element value here. So I'm appending the 1 to the path here. I'm visiting node 1. Then from here, we have to consider all edges coming from this node to all our neighbors. And we're in a fully connected graph, so every element is connected to every other one. There's no path from a node to itself. There's no self loops. But I don't have to worry about that here because we already marked it visited, right? Like if we're exploring from element 0, we've already marked element 0 as visited. If not visited, if the neighbor is not visited, then let's explore from there. Okay, so when this for loop completes, effectively a node has been fully explored. We've already visited this node, and we've visited all of its children. So at this state, at line 22, this is where earlier on in the diagram, either I marked a node as fully explored, or in the case where we want to find all paths, this is the point in time where we will unvisit it. So I'm going to backtrack and set it now to false. One other thing I'm going to do here, along with the backtracking, is pop the last element from the current path. So what this is doing is allowing for the earlier function calls to find a different path that doesn't pass through this current node. Return. So this is the backtracking portion. So this is the only change to standard DFS that's in here. Now, one other thing I have to do before backtracking, though, is check if I've actually found a valid solution. So check that I found a path of length n. So if length of path equals length of nums, so we found a permutation of length n, then paths append path. Notice I've added an array slicing operator here, and this is basically just going to force a deep copy of the path into the paths array to avoid aliasing with Python lists. So this is a little Python gotcha you have to watch out for. So I got a spelling error. Okay, so this code passed the local 3 test cases. Let's submit this. Wow, it beat 80% of users with Python 3 in terms of speed, and only 15% of users with Python 3 in space. So yeah, this approach where we're using a visited array is going to use a little bit more space, O of n extra space, as compared to some other solutions. I'll share one other solution in the code in the description that you can look at offline if you want to. But this is how to solve the permutations problem using graph algorithms, a slight modification to a very well-known graph algorithm. And it might be a good idea to know this approach anyways, where basically we unvisit a node after it's been fully explored, because this is a common way to find all paths in a graph, and you'll likely need that in other kinds of LeetCode problems that are like find a word in a matrix, things like that. So yeah, just to recap the key points from this tutorial, DFS and backtracking are closely related. So I use the word unvisit and backtracking as a hint to sort of make this connection for you. When you are doing backtracking to solve a question, you are searching depth first through the possible solution space, trying to find valid solutions for your problem. And this question is really cool because you can solve it with pure backtracking, and you can solve it with depth first search. And there's just that one little change to DFS turns DFS into backtracking. Another key point is that many problems can be modeled as a graph. So if you're ever stuck on a question, you can try to think about, can I represent the elements in this array as nodes in a graph, or the elements in this matrix as nodes in a graph? You hit that time and time and again with questions like number of islands. A great reason to consider modeling things as a graph is because graphs come up again and again and again, and everyone knows their graph algorithms. Your colleagues will know their graph algorithms. So if you say, I solved this problem using depth first search, they know what you mean. So in regards to that, make sure you yourself know your core graph algorithms. Make sure you know DFS and BFS. And there's a whole world out there of other graph algorithms that are used every day and are very important and also very interesting. So if you have some spare time, I would highly recommend you check out Dijkstra's algorithm, A star, which is a slight modification of Dijkstra, and Bellman, Ford, and Floyd Warshall are some dynamic programming algorithms to find shortest paths in graphs. And there's also Kruskal's algorithm and Prim's algorithm for finding the minimum spanning trees. So thanks again for tuning into LeetCode Legends. I hope you enjoyed this. Please like and subscribe. Take care.